Today, we're diving into something that secretly runs our world, systems of linear equations. This is the language of patterns. Let's get into it.
You know, when you think about these incredibly complex systems, like AI or massive data models, you might imagine something impossible to grasp. But the truth is, it all starts here. It all begins with a few surprisingly simple ideas, all working together. All right, so let's start with the basics. What exactly happens when one simple equation stops being on its own and has to play well with others? Okay, so look at this one equation, x plus y equals true. Now, this isn't telling us x is this and y is that. No, it's describing a relationship, a partnership. It's giving us a rule. So if x is 1, well then y has to be 1. If x is 0, y has to be 2. If x is, say, 5, then y has to be -3 to make it work. It's a whole universe of possibilities that all follow this one simple rule. But here is where it gets cool. What happens when we throw another equation into the mix? Suddenly, we have a second rule, a new constraint. Now our answer can't just make the first equation happy. It has to make both equations true at the exact same time. They have to work together. And when they do that, they start to narrow things down, pointing us towards something much, much more specific.
So we're talking about systems of equations, but what about that word linear? What does that actually mean? Well, it all comes down to the simple, powerful, predictable beauty of a straight line.
Yeah, the name gives it away, right? Linear literally comes from the word line. In the world of algebra, this has a very specific meaning. Our variables, our x's and y's, they're only to the first power. That's it. There are no squared terms, no square roots, none of that stuff that creates wild curves. And that simplicity, that's its superpower.
And this slide just makes it crystal clear. On the left, you've got your classic linear equation. If you pop that onto a graph, you get a perfectly straight line. Simple, predictable. But look what happens on the right. Just by adding that little squared to the x, boom, everything changes. We've just jumped out of the linear world. That equation makes a curve, it's more complex, a little wilder. For now, though, we're going to stick to the clean, easy-to-handle world of straight lines.
Okay, so 2 equations are manageable. But what if you have 3, or 10, or 100? Writing them all out would be a total mess. It gets clumsy fast. So we need a better way. We need a system to bring some order to all this complexity.
So, let's take a look at this system right here. It might look abstract, but you can imagine this represents something real. Maybe a simple economic model, or the limits on a budget. All the important info is there, it's just kind of spread out in equation form. So the big question becomes, how can we clean this up? Is there a way to, strip away the x's and the y's for a second and just focus on the numbers themselves, the numbers that are really running the show? And here it is. This is the big leap. We just take the important numbers, the coefficients, and we arrange them in a nice, neat grid. And just like that, those messy equations become this elegant, simple structure. What you're looking at is called a matrix. And honestly, this is the heart and soul of linear algebra. Now, in this new, super organized world, every number has its own specific address. It's not just a random 3 floating around. It's an element in a very specific spot. And we have a neat little way to label that spot. We call it a sub ij. So what does that even mean, a sub ij? It's actually really simple. The I just tells you the row, which is basically which equation you're in. The j tells you the column, which tells you which variable it's attached to. So if I say a sub 1, 1, I mean row 1, column 1. In our little matrix, that's the number 3. It seems small, but this kind of precise organization is exactly what allows computers to chew through huge systems like this in a flash. Okay, so we've got this neat structure, this matrix. That's great, but why? What's the point of all this? Well, the whole goal is to find a solution. We're looking for that one single point where everything just clicks. And a solution is more than just some answer we pluck out of thin air. It's a very special set of numbers. It's the one specific combination of values that satisfies the first rule and the second rule at the exact same time. It's that sweet spot where all the different constraints finally agree.
Okay, but here's a twist. You might think, all right, every system must have one nice clean answer, right? Well, nope, that's not always how it works. Turns out there are actually 3 totally different ways this can play out.
Yeah, not all systems are built the same. Depending on how those equations relate to each other, you might find one perfect solution Or you might find an infinite number of solutions, or you might find no solution at all.
First up, the one you probably expect. It's called a determinate system. Think about it visually. If each of our linear equations is a straight line, then in this case, the lines cross at exactly one spot, one single point. That's our solution, a perfect moment of agreement.
Then you have what's called an indeterminate system. This is a weird one. It happens when your two equations are actually the same line, just maybe dressed up a little differently. So if you graph them, one line is sitting right on top of the other. Where do they cross? Well, everywhere. Every single point on that line is a solution, which means you have an infinite number of them. Endless possibilities.
And last, we've got the inconsistent system. What's going on here? Well, graphically, these are two parallel lines. They have the exact same tilt, the same slope, but they're just shifted. They run alongside each other forever, but they will never ever intersect. No intersection means no point of agreement, which means no solution. They're just two different paths that will never meet.
So think about the journey we just took. We went from a single, simple equation to a whole system of rules organized into a matrix. And we discovered that these systems can have one answer, a bazillion answers, or no answer at all. This is so much more than just algebra homework. This is, at its core, the language of patterns.
And what you've just walked through, that's the front door to one of the most powerful branches of math there is, linear algebra. This is the engine that drives so much of our technology, our science, our economics. And trust me, we have only just scratched the surface.
This is the language that helps us see the hidden structure in almost everything. You've just learned the alphabet and the basic grammar. So the real question I'll leave you with is, now that you're starting to understand it, what patterns are you going to discover?